Hej och välkomna till provningarna i kursen konstruktionsteknik. I det här labbmomentet ska vi prova en betongbalk i fyrpunktsböjning och det är betongbalken jag har bakom mig. Provningen och utrustningen är samma som i kursen bärande konstruktioner och vi har då en hydraulcylinder som trycker på en fördelarbalk som ger 2 stycken punktlaster. Balken är upplagd på ett rullstöd som är fritt att rulla i horisontell led. Och vi har ett stöd som är fritt att rotera men som inte får röras i horisontellt. På baksidan av betongbalken har vi målat ett stokastiskt mönster som vi kan analysera med hjälp av det här kamerasystemet. Det kallas för DIC, Digital Image Correlation. Det gör att vi kan mäta deformationer och töjningar i balkens yta efteråt och vi får fram väldigt fina bilder på det här. Så vi kan gå in och mäta sprickvidder och sprickmönster som en del av en postprocessning efter provningen av balken. Det här systemet har 2 kameror och det gör att vi kan mäta i 3D-rymden. Vi mäter lasten i belastningen med hjälp av en lastcell och den lasten vi mäter är totala belastningen för båda lastpunkterna. Balken är en konventionell betongbalk med en armeringskorg. Den har dragarmering i nederkant, tryckarmering i överkant och tvärkraftsarmeringarna vid sidorna. Tvärkraftsarmeringen finns ju till för att ta upp 7 krafter. När vi provar så kommer vi belasta då med 2 hastigheter, 3 mm per minut, upp tills dess att armeringen flyter. Och efter flytgränsen på armeringen så kommer vi öka hastigheten till 12 mm per minut.
Now the beam will start to be loaded according to the test setup that Sebastian has explained. We have 2-point loads situated at 900 millimeters from the supports with a total effective span of 2700 millimeters. At the bottom of the video we can see the overall behavior of the beam. On the very left we have the load crack width for 2 different cracks. The load displacement followed by the load displacement curve measured at the center of the beam at the mid-span. And then we see the sectional behavior for the critical cross-section. Basically, we can see the stress distribution at the cross-section and the active parts of the cross-section. So now we see that the cracks start developing. So we have reached the cracking moment at some of the cross-sections. And now we are heading towards to stadium 2, where we have fully developed cracks at the different parts of the beam. So now we have linear elasticity in the materials as well as for the stadium 1. So steel and concrete are in linear elasticity. We can see that in the load displacement curve, where we have a fairly straight line, which indicates that the relation between the materials and the deflection is linear elastic. And then we can see that the stresses, as we are increasing the loads, they increase as well, so we get more stresses at the steel in tension, at the steel in compression, and as well at the concrete in compression. So now we can see that the beam is fully cracked, so the cracking has fully developed all around. So we are in a steady situation where the crack spacing is already stable, so we don't get cracks. What we do basically is to open more the cracks that we have already developed in the beam. So we will have this behavior during the whole stadium 2. So the neutral axis will remain constant at the same position during the whole stadium 2, during the whole loading phase, until we get a change in the material behavior. Then we will need to find a new equilibrium, and then we will need to change the position of the neutral axis to reach this equilibrium. As we have pure bending, we can assume that the position of the neutral axis is the same as the center of gravity in the cross-section. Basically, it is determined by the equilibrium of areas in compression and in tension. And this position is around 83 millimeters. Now we are reaching the design value for the load in serviceability, which is about 60% of the failure load, as we have considered. So at this point we have a deflection of 11-12 millimeters and a crack width of around 0.2 millimeters, a bit lower. So those are the values that you need to compare with your hand calculations. Point, we will continue loading the beam up to failure. So we will remain in stadium 2 for a while more until we overcome the limits in the stress level for the different materials. So now concrete has overcome the 60% of the strength of the material in compression. So it is basically losing the linear elasticity. So if we unload from this point the beam, we will have some remaining deformation due to that the concrete has overcome this stress threshold. So still we have some linear elasticity in the steel, so we are reaching the yielding right now. So what we will see is that due to this yielding, we will get larger crack width. So the crack width will increase a lot because we accumulate a lot of deformation at the reinforcement level. However, we accumulate deformation without being able to increase the load. So that basically means that we need to reach a new equilibrium, so we need to have variations in the neutral axis in order to be able to preserve the equilibrium in the cross-section and take the moment that is applied. So now the steel has started yielding, so we have come into the yielding strain for the material, but you can see that this yielding doesn't occur. It does not occur all around at the same time. So we can see as crack number 1 is fully yielding because we increase the crack width a lot, but still crack 2 is not fully yielding. At this point we can see that the neutral axis has started to change slightly to reach new internal equilibriums at the different cross sections. Some of the cross sections remain with the neutral axis of stadium 2 more or less, but some others has actually raised up the position of the neutral axis. And why this happens? This happens because when we need to reach equilibrium for larger moments, as the force at the steel reinforcement is constant because we are in yielding, we cannot take more forces with this steel reinforcement, then the only way to increase the moment capacity of the cross-section is by increasing the level arm. So that means that basically we need to push upwards the neutral axis, overload the concrete and the steel reinforcement in compression a bit more, and then we can reach an equilibrium for a higher moment at the cross-section. Of course, we cannot do this in an unlimited way, so there is a limit of how much we can raise the neutral axis upwards, and that's basically when we develop failure at one of the materials. Point, the neutral axis is at its highest position, so now we have high nonlinearity in both materials, and then everything is becoming a bit out of control. Some of the cracks are getting inclined due to the contribution of the shear in the shear span, and then new cracks are overcoming in the concrete. Now we have going to reach the maximum load level that we can apply in the beam. So from now on, that what happens is that we will lose capacity in the beam. And why so? That's basically because we have reached failure at one of the materials. In that case, everything indicates that we have reached failure in the concrete. So what happens is that we are losing height of the cross-section. Basically, we are losing level arm. And that basically means to lose bending capacity. Now we can clearly see as some of the concrete cover in the critical cross-section next to the loading point is falling apart. So we can see that we have actually lost height of the cross-section, and that's why we have lost capacity, bending capacity. So what happened next is that we lose even more capacity, so we cannot reach equilibrium any longer, and that's because we develop buckling of the steel reinforcement in compression. When that happens, it is not possible to reach new equilibriums because the loss of cross-section is too high, so we need to dramatically lose capacity. we unload the beam, we see that we get some remaining deformation and some remaining crack width. And that's because we have reached yielding at the steel reinforcement. And this deformation we cannot recover unless we can apply a load in the opposite direction. I hope you have enjoyed the video and thank you for your attention.